Section 2 is all about solving word problems, about taking words and turning them into numbers and variables and then solving. In fact, sometimes I feel like the main problem that some students have with math is not that they can't do the math, it's that they have trouble reading. And when you're doing word problems, it's really important to pay attention to pretty much every detail. Now, there are some basic steps in solving a word problem that uses linear equations. So first off, you need to read the problem to find out what is known and what is not known. Sometimes making a list or a table or a drawing will really help you organize and visualize those knowns and unknowns and what it is you need to find out. Assign a variable or variables to the unknown quantity or quantities. And you can use any letters you want. You can use X and Y, or you could choose letters that go with the things that you're looking at. For instance, maybe if you're looking at something that involves how many dimes and quarters, you use D's and Q's to represent the dimes and quarters. Write out an equation that relates the known values to the unknown variable or variables, and then solve just as we did in the last section, and then verify that the solution to the equation is the answer to the original problem. One of the nice things about this particular step is that you can always check to see if your answer works. You don't just go through it and then say, okay, I have an answer. You put it back in, and does it make sense? Does it make the problem work? So we're going to look at a couple of examples real quick. The first is 7 more than twice the number is 39. Find the number. One of the things that's important when you're writing out an equation is to write it just as the words are. Now, we need a variable, so we want a number. We can use n for number. And then our equation follows the words. So 7 more would be plus, twice a number. So since we said n is a number, 2n for twice a number. Anytime you have an is, that is an equal sign, and then the 39 at the end. So here we have 7 more than twice the number is 39. We've written the equation out just as the sentence was written. All right, then we go ahead and solve it. We can move the 7 over by subtracting 7 from both sides. That gives us 2n equals 32. And then divide both sides by 2, and we get n equals 16. Now, here's where we can verify. Plugging it back in, does 2 times 16 plus 7 equal? Yes, it does. 32 plus 7, 2 times 16, 32, and 7. That gives us our 39. Check. Okay, here's another one. Mark's vegetable garden is in the shape of a rectangle, and he can enclose it with 96 feet of fencing. If the length of his garden is 16 feet more than 3 times the width, find the dimensions of his garden. Now, one of the things that can help in a problem like this is to make a drawing. Make a rectangle. And when you're putting things in, we know we've got a width, and we know we have a length, but the length is 3 times the width plus 16. 16 more than 3 times the width. And so we can actually label that diagram. Now here, what's known is the perimeter is 36 feet. Now, here's the thing. Problems like this are not necessarily going to tell you the equation for a perimeter. Perimeter is just add up all the sides. In this case, a rectangle will have 2 lengths and 2 widths that are the same. But you may find that in other problems, as we go through the book, they don't tell you what the equation is. And you may need to look up what is the area for a triangle or something like that. Now that we have this, we can go ahead and do some substitution. Since L is 16 plus 3W, we put that in for L here. Now we have one equation with one unknown. That's the only kind that we can solve at this point. Combine like terms after we distribute, and eventually we end up with the width is 8. Now, that's the width. We want the dimensions. So we need to make sure and go back in with that 8, because again, our length is 16 plus 3w, and plug that back in. So we get 3 times 8 plus the 16, that's a 24, so the length is 40. And then we can check 2 times 8, the width, plus 2 times 40, that's 16, and 80, that gives us the 96, so that does work. A couple other problems that we'll have in this section. Interest problems. And we're going to have the most simple kind of interest problems. They usually involve just 1 year as opposed to multiple years. But basically, the equation for interest is I, interest, equals P, principal, times the interest rate, the annual rate, and then the number of years. If an investor deposited $3,000 in an account that paid 2% annually, how much is in the account after 1 year? So there's the 3,000, that was the principal. Notice that we wrote the percent as a decimal. So what was 2% becomes 0.02. We move the decimal twice. And then here's our 1 year. So we do that, we make $60 in interest after the 1 year. We started with 3,000, so 3,000 plus the 60 gives us 3,060 in the account after the 1 year. And then finally, we have what's called a mixture problem. And in this example, the mixture problem involves mixing two solutions that have different concentrations. And usually what they want is to have the mixture have a certain concentration at the end. So the general type equation for this is we take the percent of solution 1 times how much we have of solution 1 plus the percent of solution 2 times how much solution 2 we have. And then that equals the final percentage times the total amount. So let's look at an example real quick. A chemist has two solutions, one that's 20% alcohol and a second that's 30% alcohol. So these are our two initial percentages. She wants 40 milliliters of a solution that is 24% alcohol. Notice that we want an amount that is not simply just the average of those two percentages, 20 and 30. So how do we get there? Well, you might say, but I don't know either amount. How am I supposed to get there? But what we do know is I want to have a total of 40. So if I say I have X amount for the first solution, then the rest of it has to be the second solution. So first off, my 0.2, that was the 20%. My 0.3, that's the 30%. X is however much of the 20% I have. 40 minus X is the rest of it. Because again, they got to add up to 40. Here's my final percentage and then the 40 milliliters total that I wanted to. So now, written as an equation with a little bit of distributing and all, please note I'm going to end up with 0.1x because I have 0.2 here and a negative 0.3. So I have negative 0.1. 12 because I have 0.3 times the 40, that gives me the 12. And then 0.24 times the 40, that gave me the 9.6. And then I can solve for what x is. And it turns out that x is 24. So 24 milliliters had to be at the 20%. And the rest, 16, had to be at the 30%. So these are some of the basic kinds of problems that we're going to solve in this section. So let's start off with problem 1. Michael has nickels and dimes in his pocket. He has 5 more dimes than nickels. If Michael has $202.30 in his pocket, how many nickels and dimes does he have? So first thing is he has 5 more dimes than nickels. So the dimes are going to equal the nickels plus 5. So note I have dimes, D for dimes, N for nickels. Now, every dime is worth 10 cents. Every nickel is worth 5 cents. So I can also write out 0.05 for 5 cents times the number of nickels plus 0.10, 10 cents, times the number of dimes has to equal $2.30. Now, the first thing is I see I got decimals. I don't want decimals, so I'm going to multiply everybody by 100 to get rid of my decimals, and I'll end up with 5n plus 10d equals 230. Now, I cannot solve this just as it is because I have 2 different unknowns, the nickels and the dimes, but I have a relationship between nickels and dimes, and so I'm going to do a substitution. So I'm going to rewrite this as 5 nickels plus 10 times nickels plus 5. So notice what used to be a D is now the n plus 5, and then I still have my 230. Now I have one equation and only one unknown, and so I can solve, first distribute, so 5n plus 10n plus the 50 equals 230. Subtract, combine the 5n and 10n, subtract 50 from both sides, will give me 15n equals 180. Divide by 15, and I'll end up with n is 12, which of course means that the d equals 17. 12 nickels and 5 more dimes, 17, and of course I could check real quick, 17 dimes, that's 170, or $1.70, 12 nickels, that's 60 cents, $1.70 and 60 would give me my 230, and so there are my answers for the first one. Now, one of the things to note in a problem like this is sometimes you'll get a problem in which you can do all the steps just as I've done them, and then you'll solve for your n is 12 in this case. But what the question wanted to know was how many dimes. So you always have to make sure and go back and check. Do they want to know both coins? Do they only want to know one coin? Is it the one I've already solved for? Or is it the other one? All right, next, Caitlin drove to visit her brother at a rate of 60 miles per hour. On the way back, she drove at a rate of 75 miles per hour. If the return trip was 2 hours less than it was getting there, how far away does her brother live? Well, this is a velocity problem, and velocity is distance over time, which can be rearranged to show the distance is velocity times time. It's kind of like, if I'm going 60 miles an hour for 2 hours, I'll have gone 120 miles. So 60 times the 2 to give me the 120 miles. Now, trip there, and again, little pieces like this can help. The trip there, well, my D is going to equal 60 times however long it took. My trip back, the distance is going to be 75 miles per hour. However, it took 2 hours less. And so I needed T minus 2 there. Now, we're making the assumption that she took the same trip there to get back, and therefore these two T's are equal, and so I can now go 60T has to equal to 75 times T minus 2. First, get rid of the parentheses. 60t equals 75t minus 150. Do a little rearranging. Minus 15t equals minus 150. Subtracted 75t from both sides. Divide both sides by the negative 15, and t will equal 10. So now I've solved my equation, but again, this is not what the problem wanted. They don't want to know how many hours. They wanted to know how far away. So I could simply go, all right, my d is 60 miles per hour times my 10 hours, and d is 600 miles. By the way, if I had used the other form, the 75 here, 10 minus 2 would be 8. 8 times 75 would also give me my 600 miles. So you got to always check, after solving your equation, have I actually answered the problem? All right. 3 consecutive odd integers, and their sum of the smaller 2 integers is 49 less than 3 times the larger amount. Now, before we, get into the actual equation, if you just think about any 3 odd numbers, like 3, 5, 7, now I should say any 3 consecutive odd integers, 3, 5, 7, or 11, 13, 15, well, what do you notice about them? They're all 2 apart. 3 to 5 is 2, 5 to 7 is 2, 11, and so they're always. So I can generalize and say, my first odd number is going to be n. My second odd number is going to be n plus 2. And my third odd number is going to be n plus 4. So 3 plus 2 gives me the 5. 3 plus 4 gives me the 7. 11 plus 2 gives me the 13. And 11 plus 4 gives me the 15. So I have this way to represent 3 consecutive odd integers. Now, we want to write out an equation that follows the words. Okay, the sum. Sum means add. The smaller 2. Well, these 2 are the smaller 2 because that's got a plus 4 on it. So I'm going to put in some parentheses, mostly just to separate. So there's my sum of the smaller 2. And then that says that equals, again, is an equals. Is equals. Now it said 49 less than. We had more thans in some of our examples, but when we do a less than, then that's the subtract. 3 times the larger one. Well, the larger one is n plus 4, so we want 3 times that. And then less than, well, we have to subtract the 49. Now, these parentheses, as I said, are just to kind of help us bracket things. So here's the first number, there's the second number, there's 3 times the third number. So adding these, I'm going to have 2n plus 2. And then over here, I have 3n plus 12, subtract 49. Okay, so putting those 2 together, I have 3n subtract 37. Now, even though I usually put the variables on the left, in this case, since I have 2n here and 3n there, and I just subtract 2n from both sides, that's going to give me n on the right. And then I'm going to add, so that'll leave me n minus 37 equals 2. Now I add the 37 to the other side, and I'll end up with n equals 39. So if that's n, then plus 2 plus 4, and there are my 3 consecutive odd integers. Okay, problem 4. For a matinee, movie theater charges $4.50 for children and $6.75 for adults. If there were 20 more children than adults and total receipts were $405, how many children were at the matinee? So, children and adults. And again, there are 20 more children than adults. The children cost $4.50 a ticket. The adults, $6.75 a ticket. And it comes to $405 altogether. Note, by the way, how similarly I set this up to the first problem. Numbers are slightly different because I'm doing different prices of tickets instead of dimes and nickels, but I've set it up exactly the same way. Okay, now I'm going to multiply everybody by 100 to get rid of my decimals. Now I'm going to do my substitution. In this case, I'm going to substitute for C, because C equals A plus 20. So, plus 675A equals 40,500. Again, this is the same as this. I've just substituted in for C. Now let's go ahead and distribute. Okay, I'm going to combine the 450 and the 675. That'll be 1,125. Subtract 9,000 from both sides. And that'll give me 31,500. Divide both sides by the 1125. And I have 28 adults. And since there are 20 more children, I have 48 children. Now please note, I solved for A, but the problem actually wanted to know C. It wanted to know how many children. All right, let's look at an example of an investment problem. Jessie was given $35,000 when she retired. She invested some of it at 7% and some at 9%. If she earned $29.10 in interest in 1 year, how much was invested in each account? And here we can make a little table to help us. So principal, the rate, the interest rate, and the time. So again, here's X for how much was in the first account, which we're going to say was at 7%. So notice I use 0.07 time 1 year. The other one, well, it's got to be what's left. So the 35,000 minus X was at 9%. Well, it'd be great if you could get these interest rates today instead of something like 2 or 3 at best. And so now I have a way of looking at both parts. And of course, we want to know how much was invested in each part. But what we know is this was the total that she earned in interest for the year. So that means it has to be this much from the one account, and then this much from the other account. And of course, since they were both for 1 year, it's just a 1 there, and that has to equal the 29.10. Okay, we're going to multiply everybody by 100 to get rid of our decimals. That'll leave us with 7x plus 9 times the 35,000 minus x. Again, did not touch the number inside the parentheses, and that has to equal 2910. And just add 2 more zeros. That's the nice thing about multiplying by 100. All I need to do really is think in terms of zeros. Okay, now distribute 7x plus 315,000 minus 9x equals 291,000. 7x minus the 2x minus the 9x will give me negative 2x. Subtract the 315 from both sides. That gives me negative 24,000. Divide both sides by negative 2. My x is 12,000. So that means I had 12,000 at 7%. And then the rest, which would be 35 minus the 12, 23,000 at 9%. By the way, in some problems, you find that you need to label. In other words, you can't just say my amounts are 12 and 23, because one of them is at 7 and one of them is at 9, and if you're not saying which is which, it's not clear to the grader exactly what you found. So you need to actually specify, like here, A for adults is 28, C for children is 48. All right, now we have an example of a mixture problem. Okay, now I could set this up similar to what I did here. So solution 1 is at 6%. I don't know how much, so I'm just going to say it's x. Solution 2, that one's at 9%. Okay, now I want to get to 72 total. So whatever x is, the rest has to be in solution 2. So I'm going to do 72 minus x. Notice how similar that was to really what I was doing in the interest problem, the one above. It really is a mixture problem. Now we can put things together. Again, the percentage of the first times its amount plus the percentage of the second one times its amount has to equal the final percentage times the total amount. This goes right back to doing our mixture problems. Okay. Percent solution 1 times amount of solution 1 plus percent of solution 2 times amount of solution 2 equals final percentages times total amount. Going to multiply everybody by 100 to get rid of the decimals. So I got 6x plus 9. 72 minus x equals 85. Let's see, 8.85. Ooh, I needed to really do everything by 1,000, not 100. 3 decimal. So really, that needed to be 60x, and that needed to be 90 times the 72 minus x. And then this will just be 85 times the 72 minus x. So you got to count. Yes, just 2 here and 2 here, but there's actually 3 here. So I needed to multiply everybody. Multiply by 1,000. All right, so now we can distribute. And I have my 60x plus 90 times 72 is 6480. Minus 90x equals 85 times 72. Oh, wait, I didn't want this part here. Sorry about that. Going too fast. It's just 72, not 72 minus x. That part's 72. This is total. of 72. 85 times the 72 will give me 6120. Go ahead and rearrange. 60 minus the 90 will give me negative 30x here. Subtract the 6480 from both sides will give me negative 360. And divide both sides by negative 30. And so x equals 12. Now that I know that, I know that I'm going to have 12 milliliters at 6%. And the rest, well, the rest is 72 minus the 12. So we have 60 milliliters at 9%. Yeah. All right, last problem. Between 1946 and 1964, the U.S. population can be modeled by the equation y equals 2.8370 plus 140.83. The value of y is the population as of July 1st of a given year, and x represents the number of years after 1946. Thus, x equals 0 in 1946, but x equals 1 in 1947, and 2 in 1948, and so forth. What was the population on July 1st, 1952, and in what year did the population reach 150 million? Now, by the way, the population is measured in terms of millions, so y is in terms of millions. Now, 1952 subtract 1946 gives us 6. So what we're looking for is x equals 6, the number of years after 1946. Now, if you're not sure, you can always do it this way too. You can make yourself a little table, year and x. So 1946, that was 0. 1947, that was 1, and so forth. Let's see, 0, 46, 47, 40. Oh, this one's 49. Gotta make it. So 1951 is 5, and 1952 is 6. So now, if you were doing 30 or 40 years, that probably is not very practical, but you can do that to help you keep things straight, especially when you don't want to include the first year. So now we use my equation, y equals 2.8370 times the 6 for x plus the 140.83. That gives us, using my calculator, you can always use your calculator, 157.852 millions. Or, if you wanted to write it out as a regular number, something like that. So that's the first part. Second part, now, when or in what year would the population reach 150 million? Well, that's the y. So we're going to take our equation and plug in 150. Parentheses is just I'm plugging it in for that. And then we're going to solve for x. So I've rewritten the equation, but now I need to find out x when that gets to 150. So subtract 140.83 from both sides gives me 9.17. divide both sides by the 2.8 number, and I end up with 3.2326x. So, 3 years later, that's in 1949, so it'll reach 150 million in 1949. And since this is always done in response to July 1st, if we had been more than 0.5, then that means we would have also been more than half a year, which would have put us into 1950, just early part of the year. But since we're less than halfway, we are still within the year 1949. And so some examples of doing word problems.